So welcome everyone. I'm really excited to be able to welcome you this morning to actually the second idea talk. So the second session of our 2020 environmental gathering here at Alberta EcoTrust. This is an especially exciting session as with our first idea talk and this one we're partnering with the City of Edmonton to present some research that was funded through a grant program. So I will talk about that in a minute, but before I do that, just wanted to introduce myself to folks that are on the line. To those of you I haven't had the pleasure of meeting yet, my name is Simon Irving and I am the program manager at Alberta EcoTrust Foundation, and I will be acting as sort of your host for this morning. I am joined with a couple of my colleagues, Vicky Stroich, who has her camera off right now, but you'll be hearing from her in a moment. Oh, there she is. Hi, Vicky, and also Tegan.
Hi, everyone.
And so they are the engagement director and communications lead, respectively, for Alberta EcoTrust Foundation. I'm also joined by my friends at the City of Edmonton, and in particular Barbara Daly, who you see there out in the galaxy. And so you'll hear from Barbara in a moment. So our first presentation is looking at climate models in Edmonton. And we have a multiple choice question for you. I suppose it's a poll, but a bit of a quiz too, which is according to climate models on a provincial scale by the 2080s, conditions in Edmonton are most likely to support ecosystems that we currently see in A, Medicine Hat, so dry grassland vegetation, B, Vancouver Island, so a more wet and temperate rainforest climate, or C, Fort McMurray, a cool boreal forest. So as folks are starting to answer that, and please do choose wisely, I'll go ahead and introduce our first speakers. So Dr. Dave Sauchyn is the director of the Prairie Adaptation Research Collaborative at the University of Regina and a professor of geography and environmental studies. His research interests are one, how knowledge of climate and hydrology of the past millennium can inform our understanding of future climate and water supplies. And secondly, a planned adaptation to minimize the adverse effects and impacts of climate change. Dave has given more than 350 invited presentations on climate change and co-authored about 150 papers and book chapters. So he was born, raised, and educated in Edmonton. Today, Dr. Sauchyn is joined by Dr. Soumik Basu, who is a research associate at the Prairie Adaptation Research Collaborative, or PARC, and the Department of Geography and Environmental Studies at the University of Regina. His area of expertise includes regional and global climate modeling, dynamical downscaling, extratropical cyclone variability and dynamics, climate extremes and hydroclimate in the prairie regions, Arctic climate variability, future climate scenarios, the interaction between Arctic climate variability and mid-latitude climate, and of course, Eurasian mid-latitude cyclone variability. So we are in very, very good hands here. Dr. Soumik has an MSc in Atmospheric Sciences from the University of Kolkata, India, and a PhD from the University of Alaska, Fairbanks. And prior to moving to Canada, he worked at the International Arctic Research Center in Fairbanks, Alaska, for many years. So I'm glad I made it through those two bios because they are quite extensive and lots of big words there. So we're very excited to hear from their research. But first, let's put up the poll results. Yes, which is, I think, overwhelmingly Medicine Hat, which is the correct answer. So great job. Looks like there were 46 people that got that correct. So that was perfect. And with that, I'm happy to hand it over to Dr. Sauchyn. Please take it away.
Great, thank you, Simon.
Your slides look great.
Okay, good to know. Yeah, and you can hear us clearly?
We can.
Great. Well, thank you for that introduction. Soumik and I are pleased to present a description of our research project, the high-resolution climate change projections for the City of Edmonton. This is an 18-month project. We're 1 year in, so we will provide final results next spring, and we hope to be able to travel to Edmonton to give the presentation in person, but that remains to be seen. In the meantime, we have some preliminary results. We have some results that are hot off the press. And what we propose to the City of Edmonton is that we would provide projections of the future climate for key variables at a municipal scale. And that's important, that we are presenting information at a suitable scale for urban planning. And this includes shifts in the probability of extreme events, information on climate risks, guidelines for translating the science so it can be used for engineering and planning, and finally, a plain language summary that we'll produce so we can communicate to Edmontonians and the wider public concepts like risk, uncertainty, and resilience. We are based at PARC, Prairie Adaptation Research Collaborative, which was established 20 years ago to do this kind of research. Research in climate change, but which is in support of science-based adaptation planning. So our research with the City of Edmonton is very much within the mandate and the type of research that PARC does. Here's a couple of maps of Canada from a report that was released by the Government of Canada last fall, showing the change in temperature across Canada since 1948. If you can't read that legend, the temperatures are all above zero, but the higher temperatures are in the red and almost black colors. Excuse me. The thing to note is that the most rapid rate of warming in Canada is in northwestern Canada, including parts of northern and central Alberta. But the greatest amount of warming is in winter. So if we look at winter temperatures, and in particular the daily low temperatures, this is the record for Edmonton right back to 1880 when the weather station was established. And there's been a dramatic increase in minimum winter temperature, an increase of 6.5 degrees, which is unbelievable actually, such that in the last several decades, there really hasn't been a cold winter. Now it's hard to convince people that the winters on the prairies are not cold, but the most recent really cold winter, you have to go back to that spike pointing down to -26, which was the average daily minimum temperature. That was in 1969, and I remember it well because I was there. All of the school children in Edmonton got a certificate from the Edmonton Journal certifying that you survived the winter. And that certificate included the temperatures that were recorded in Edmonton every day. And over a period of 26 days, the warmest it got was -21. And of those 26 days, 21 of them, the warmest it got was -30. 21 days of less than -30. It's just hard to fathom. It's hard to imagine a winter these days that could be this cold. And in fact, it couldn't be because of global warming. Well, this is a bit of history. We don't have data for the future, unfortunately. And so we have no option but to model the future. And scientists model the climate of the future at 2 scales. There are models that simulate the climate of the entire world, these global models, using a grid that covers the globe and extends up into the atmosphere and down into the ocean. And then there are regional climate models that simulate the climate of a smaller area, but at higher resolution. And so what we propose to the City of Edmonton is we would provide them information from these regional climate models. And just to give you a sense of the difference in scale, this square represents the grid from a global model. So looking at the previous diagram, what we're showing is a single grid cell over central Alberta. And so if you use information from a global model, it's averaged over that area. But we can scale down to a 30-kilometer grid and provide a future climate for each one of those grid cells. We can scale down to 10 kilometers, and now we have many, many, many future climates in the area covered by a single cell from a global model. And what Soumik has been doing is scaling down to a grid of 3.3 kilometers so that we can provide the City of Edmonton with actually hundreds and hundreds of future climates, one for each one of those cells. So I'm going to turn things over to Soumik, and he's going to tell you how he's been able to simulate the climate of central Alberta at this scale.
Thank you, Dave, for the nice introduction. So I'm going to start with a little introduction about the regional climate model that we are using. So that model is called Weather Research and Forecasting Model, or in short, WRF. That model was developed by the National Center for Atmospheric Research, located at Boulder, Colorado, and many other US institutions. WRF model is popularly used for atmospheric research and for operational forecasting applications. The National Weather Service in US use WRF for most of their forecasts. So how a climate model works? It has several steps. So the first step for the working of a climate model is to set up the domain. We need to select which region we want to simulate. Then we need to provide the meteorological data for that region. And after that, the model has several pre-processing steps in which the model interpolates that input meteorological data to fit the model's grid both in horizontal and in vertical. After that, the model used time integrations to simulate the climate starting from one point of time. It starts simulating the climate for suppose next 10 minutes, and so then from that 10 minutes point, it simulates the next 10 minutes, and so on. And how the model does that? It has many equations embedded in its codes, which includes the radiational feedbacks from the atmosphere, which includes long wave and short wave radiation. Then it includes the feedback from the cloud. It includes precipitation, temperatures, the effect of albedos, effect of ground snow cover, effect of the evaporation, transpiration, aerosols, and many other factors. So after considering everything in its equation, so the model finally gives us the output for our desired time. Suppose we can control that, so we can get data outputs 6 hourly, monthly, so how we want. So how the model output looks like. So it gives us the outputs in 3D and 4D. So when we visualize that it looks like that plot that was showing there. So it gives us the distribution of the variables that we need over the space. And it moves from latitude, it has latitude and longitude, and it can also provide the data for the verticals. So the most important thing for an experiment is the domain selection and input of the meteorological data. So for our experiment, we used something called nested domain, which is like domain within domain. So from the input of 100-kilometer resolution, we first made it to the 30-kilometer. Then we lowered it to 10-kilometer and further to 3.3 kilometer. As our input, we use bias-corrected climate model output from NCAR's Earth System model, Community Earth System model. And for our experiment, we did 2 sets of experiments. One is historical, which goes from 1st January 1975 to 31st December 2005. And the other one is called representative concentration pathway, which is the future scenario, or it's called RCP 8.5. So that simulation goes in our experiment from 1st January 2021 to 31st December 2080. So we have this future time period of 60 years. So, and we got outputs of 6-hourly output of many variables such as 2-meter temperature, precipitation, snowfall, snow depth, surface runoff, soil moisture, radiation, humidity, sea level pressure, and many others. So in our experiment, we have the highest resolution for the Edmonton at 3.3 kilometer. So what did we get from our experiment? So first of all, the resolution got better. As you can see here, that from 100 kilometer, we moved to 30 kilometer to 10 to 3.3. So these panels on the left, the four on the left-hand side shows the changes in the air temperature, and on the right-hand side, it shows the precipitation. So the first one on the upper left corner is how it looks like from the global climate model. So one grid cell covered everything. So then we move to the 30 kilometer. Now we can see some changes in the upper right corner and the lower left corner of the domain. Then when we move to the 10 kilometer, which is the lower left, we can see there are now, it's showing changes over the city of Edmonton too. And when we move to 3.3 kilometer, now we can see the details of the changes, that the northeast corner of the city of Edmonton has been the colder, and there has been, as you move to a southwest, it's getting warmer. And the same goes for precipitation also. So as we move from high resolution to lower resolution, more and more changes become prominent. So next, we looked at the changes in the precipitation between the near future period, which is from 2021 to 2050, and the far future, which is from 2051 to 2080. So in the near future, we can see that, and in the panels, in the left panel is for the near future, and the red colors stands for drying, and the blue color is for wetness. So we can see that in the summer months, in August especially, there is a very intense the dryness in between enhanced dryness, and in November. But as we move to the far future, we can see that there is more dryness over almost now over July and August as well. So the summers are getting more and more dry as we move forward towards the end of the century. But in the winter months, we can see that in December and January, those are getting wetter. And if we look at the air temperature, we can see the biggest change in the air temperature in the near future, and in the near future is in the months of January. And here I should mention that all the changes are in positive. We didn't see everything is in positive. There has been warming in every month. So the blue color is less warming, and the red is the more warming. So, and as we move towards the end of the century, there is more and more warming become more prominent, and everywhere it's just warming more. And it depends, ranging between 1.5 to 5 degrees centigrade. So, and for the conclusion now, I'll hand it over back to Dave.
Thank you, Soumik. Some very technical work that Soumik is doing, but we can summarize it in this last slide. And maybe a basis for further discussion is that we engage with the City of Edmonton in order to provide them with this very detailed information on how the climate is changing, because previously they had information only at the global scale. And we were inspired to work with Edmonton because it's probably the most progressive city in Canada and one of the most progressive cities in the world when dealing with climate change. We consider this research important because by preparing for climate change, Edmonton and Alberta can prevent significant damage and losses from climate change. And it's at the municipal scale that governments make decisions that affect our everyday lives. We were surprised to discover so far the large degree of variability of climate in the Edmonton region, both over space and over time. And this study of Edmonton will serve as a model, working with the city, providing the city with this information. It's really a model of how cities should respond to climate change. We hope that the city and the citizens find the results useful and interesting, and we hope that we're able to inform policies and practices that make Edmonton a more resilient city. That's it. Thanks.
That's great. Thank you so much, both of you. I really appreciate that. But first, we're going to start with another quick poll for you here that relates to our next topic, which is fire risk modeling. We can go ahead and display that poll. And there it is. How prepared are you to evacuate should a wildfire occur in your community? Prepared, not prepared, or unsure? So unlike the first poll question, there's no right answer here. Please go ahead and respond. And as folks are starting to respond, I will go ahead and introduce our next set of researchers. So we are joined today by Dr. Tae Kwon, who is joining from the Department of Civil and Environmental Engineering at the University of Alberta as an assistant professor in 2016 after receiving his PhD from the University of Waterloo with the prestigious doctoral dissertation award. Dr. Kwon's research focuses on winter road maintenance, location optimization of intelligent transportation system facilities, geomatics, spatial and temporal analysis of road traffic and safety using big data and deep learning. Dr. Kwon has published nearly 60 papers, including peer-reviewed journal and conference papers, project reports, and book chapters. Dr. Kwon received the 2019 Great Supervisor Award for excellent supervisory contributions. In 2020, Dr. Kwon was awarded the Faculty of Engineering Early Career Research Award in recognition of excellence in research and his influence at both national and international levels. Dr. Kwon's research has been supported by many different organizations, including NSERC, Alberta Transportation, Iowa Department of Transportation, CEMA Plus, and of course, the City of Edmonton. So Dr. Kwon will be presenting his research this morning, and he will be joined later on during the Q&A session by his colleague, Dr. Karim El-Basyouny, for the question and answer period. So I did actually just want to take a moment now to introduce Dr. El-Basyouny, who is an associate professor and inaugural City of Edmonton Research Chair in Urban Traffic Safety at the University of Alberta. He's the co-founder and steering committee member of the Center of Smart Transportation. He's an active member of multiple international and national safety committees and serves on the editorial boards of several prominent journals. His research program is focused on the integration of statistical inference, computing techniques, and machine learning to extract information from huge data sets to address safety trends and patterns, forecast potential collisions, and make evidence-based safety decisions. Over the past decade, Dr. El-Basyouny's research has been supported by all levels of the Canadian government and industry. He's published 123 peer-reviewed publications, was invited to present at 39 workshops, seminars, and panels, both local and international. Dr. El-Basyouny has won several research awards throughout his career, with the most recent being the 2020 U of A's Faculty of Engineering Mid-Career Research Award and the 2020 Canadian ITS R&D/Innovation Award. And I am actually surprised, based on getting ready prior to this call, that you don't have your prolific PowerPoint skills listed in your in your bio. But with that, we will go ahead and show the poll results before I hand it over to Tae. Okay, so looks like 9% of folks feel prepared, 68% of folks are not prepared, and 23% are unsure. So a little bit of variability across there, but I think largely folks are skewing in the not prepared. So interesting results there. And with that, I'm going to go ahead and pass it on to Dr. Kwon.
Perfect, Simon. Thank you. So do you see my screen well, and then my sounding okay?
We can see and hear you just fine, yes.
Oh, perfect. Okay, sounds good. Okay, Simon, thanks for the introduction again. Good afternoon, I guess, right now. Good afternoon, everyone. As introduced, my name is Tae J Kwon from the U of A. And then today I want to present to you our ongoing Cities Legacy IPCC research project entitled Diverting Risk, Supporting Climate Resilience Through Fire Risk Modeling Within the City of Edmonton. So before I begin, I would like to credit our research team for their support in making today's presentation possible. So Mohammed Al-Zaburi, who is working as a graduate research assistant, and also my colleague, Dr. Karim El-Basyouny, who is also acting as a principal investigator of this project. So as we all know, wildfire impacts are detrimental and very costly. as it affects not only our ecosystems, but biodiversity, as it destroys or at least damages the habitable or adaptable land for animals and plants. A wildfire also entails substantial economic losses for example, for rebuilding communities and infrastructures. And also lastly, the effect of the smoke and dust can also cause intense breathing discomfort, whereby negatively affecting our health. And then we also know that the wildfire have contributed to fatalities, especially impacting the firefighters, lifesavers working on the front line. So I think the previous, professors from Regina actually did a fantastic job. The climate change is happening as we speak. And as a result, we have been experiencing an increased intensity in our annual fire season in Alberta. So with the continued increase in temperature that generates sort of a dry fuel to burn and more frequent lightning strikes to start the fires, the wildfires actually remain a large risk to all of us. So a U of A forest fire researcher, Dr. Fleggen, says that Canada's future looks pretty smoky because the climate change will trigger a lot more fire in the future and thereby affecting and more Canadians. So the others also predict that the Western Canada, including Alberta, will see a 50% increase in the number of dry and windy days, which would intensify the wildfires and spread as well too. So we all know the recent devastating incident that happened back in 2016 in Fort McMurray, that a wildfire destroyed many homes and buildings and forced many people to evacuate, that resulted in huge financial loss. And one interesting study by one of our close colleagues in transportation group at the U of A, Dr. Amy Kim, and her research team conducted a study that evaluated evacuation responses of the Fort McMurray incident. And then she concluded that the secondary route, as you can see here, the Highway 881 was underused actually during the first 12 hours of evacuation. And also stated that use of this route might have reduced the traffic congestions and possibly facilitated more timely evacuations. So in our city of Edmonton, we have the largest stretch of parkland that runs directly through the urban area. And also we have to considering the proximity of the river valley that runs through both the residential and commercial areas, we are exposed to a greater threat of wildfire. So it is this reason that our team, myself and my colleague, is working towards developing a fire risk model that can identify the location with the high potential risk so that we can better plan on responding to unforeseen fire attacks. And also equally important, using our expertise in transportation engineering background, we also want to develop a comprehensive sort of emergency response and evacuation plan and strategies in case of a wildfire attack, so that we can ensure the Edmonton will continue to remain as a climate resilient city. So prior to developing a fire risk models, we first have to understand what factors would affect the risk of having a wildfires. So our extensive literature review has revealed that there are 4 different groups of factors that contribute to increasing the risk associated with wildfire occurrences and spread. And first, obviously, it's a climate. In particular, temperature, relative humidity, and wind speeds are correlated with the chance of having a fire occurring, because of hot, windy, dry conditions tend to result in higher probability or likelihood for a fire to start and ignite. Another major factor affecting fire occurrences is anthropogenic or human factors. In particular, incorporating land use informations is really critical to determine the risk associated with the fire occurrences and spread. And we also consider the proximity to roads and rivers because they have been found to influence the risk of wildfires. So another factor is the topography, and such as elevation, aspect, and slope, and curvature, because they may also influence the potential for ignitions and propagations of wildfires. So vegetation is the another primary fuel source for wildland fires. And then also the density of the forest and forest type, also known to affect the risk of wildfire. For instance, the higher the moisture content, the less the chance that there is for wildfire to start. So these are the primary factors that affect the wildfire. So now that we understand what factors will contribute to increasing the risks, we are implementing a GIS-based fire risk modeling framework, as it has been proven, as the GIS has been proven to be a powerful tool for collecting, analyzing large-scale spatial data. Yes, as for our first step, we will collect and process all risk indicators, followed by determining their magnitude of importance or contributions to the risks using what we call analytical hierarchy process. So this, I don't want to go into the detail, but this is a well-established technique used for multiple criteria decision-making that requires expert input. So we're going to be actually using experts' input into this. We'll then use a multiple criteria analysis technique to combine all the risk indicator maps to generate final risk maps. And since it's important to be able to sort of determine the climate change extent and to generate to extent that in our fire risk forecasting or modeling process, we will also integrate two distinct long-term human climate forcing scenario, namely representative concentration pathway, known as RCP 8.5, and a business as usual case, and RCP 4.5, strong mitigations. So one of the key contribution areas, one of the key contribution area of this project will be the utilization of the state-of-the-art techniques and also the high resolution large scale data sets. So light detection ranging is LiDAR is one technology that can improve the detection and recording of the large areas. And luckily, the city of Edmonton provides a very large amount of our LiDAR data set that actually collected it. An example of the data that we processed and are shown here, you can see here, that covers the parts of Edmonton. And we will use the LiDAR data set and then also extract the main topographical feature, such as elevations and slope and aspect and so on and so forth. And also we will use it to determine the proximity to roads and river as well. Another remotely sensed data we are using is Landsat 8 satellite imagery. The satellite images are used to examine the health of a treed area, which can be considered very unique to this study, I should say. And using different band combinations, we can calculate what's called the normalized difference vegetation index, NDVI. Then we're using it to quantitatively assess the risk associated with the different tree types and their health. And you can think of this sort of as the dryness index, how dry it is, how wet it is, and so on and so forth. And since the meteorological parameter, such as temperature, precipitation, etc., are critical inputs to the models, we're using data sets coming from a total of 27 Environment Canada weather stations, which you can see here, and that are within the city and outside of the city of Edmonton. And but these are point measurements. So what we need to do, what we need is that we need to cover the entire city of Edmonton, and we will use one of the most advanced interpolation technique called kriging or other techniques to make them spatially exhaustive. So make them available over the entire study area. And City of Edmonton also provided their recently developed or updated the urban primary land and vegetation inventory called the UPLVI that contains detailed information pertaining to the city's natural assets. So that includes the forest type and soil type, and that are useful in this project. But there's so many different potential fuel that can be also included in the model as well. Just to sum up, with all the data set that we collected and processed, we will combine all these different types of data together. So road network, airborne LiDAR data sets, spatial-borne Landsat data, and so on and so forth, merge them into a 30-meter by 30-meter grid cell using a GIS platform. And obviously, this is done for efficient data handling. And like I said before, we will then generate a fire risk visualization map and possibly decision support tool for reducing wildfire threat, which I believe is crucial or instrumental for municipalities like City of Edmonton, so that they can assess the development land and manage potential fire sources. So just to sum up, upon completion of this project, our team anticipate that we'll be able to construct a comprehensive and high resolution, very detailed database for mapping fire risks, which in turn will provide city and park officials with the more detailed sort of account of our green areas and volume of trees and vegetations around the city, in and around the city. So that's one thing. We'll also develop a fire risk model by combining the use of GIS, large scale spatial data analysis, satellite and lidar remote sensing, and with the ability to identify high risk area for further investigations. With this model in our hand, we'll also be able to assist the city officials and planner with establishing a emergency response and evacuation strategies to ensure the safety of all Edmontonians, and also to ensure that our city continues to be a climate resilient city. Okay, so before I finish, our team would like to take this opportunity to express our deepest gratitude to Alberta EcoTrust for their vote of confidence in providing the unique research opportunity during this difficult time, and also financial support for us to conduct this research. And we also like to acknowledge the City of Edmonton for their in-kind contribution in mobilizing and providing data sets that are vital for the success of this project. So, and then we have 6 different individuals, experts that actively participate in our regular meetings and discussions, which have also been tremendously helpful. So I wanted to just take the moment to acknowledge these individuals as well too. So thank you very much. Here's the contact info. If you do have any questions, feel free to let us know. Thank you.
Great. Thank you so much, Dr. Kwon. That was super interesting. A big thank you to our sponsors of this 5th annual environmental gathering as we're finding our way in these unprecedented times. So thank you to Suncor, ABCRC, Alberta Views, and of course, without a doubt, the City of Edmonton for their support in all of this. Thank you also to our visionary partners. These are the organizations that are at the heart of who Alberta EcoTrust is and what we do, and we couldn't do our work without these visionary partners, so we're forever grateful for their support and collaboration on much of our work. And then last, but of course not least of all, thank you to all of you for attending today and for engaging in this work, for being interested in it, for engaging in your communities, and for being interested in this. And I hope to see you all soon at one of the other environmental gathering events. So with that, I will release you just a couple of minutes early. And thanks again, everyone. We'll see you soon.